and then MP H dot P plus VC minus VP, VP minus VC cross G. H dot C plus RC minus RP cross IC. How do I calculate the moment of a force? Right, R cross F. How do I calculate the moment of a force about a point P, not the origin? Exactly, R minus RP cross the force plus summing the moments. And how do I calculate the angular momentum of a rigid body, the HC part? Just need to put a reminder here. That's for a system, that's for a particle. What about for a rigid body? I omega, exactly. Okay. So HC is equal to IC omega. HO also is equal to IO omega. So HP, F omega is theta dot EZ, or just along EZ. This equation simplifies. HC is equal to IC X Y minus, sorry, I think it's IC XX. We derived this last time, IC XZ omega dot, right. IC XZ omega dot minus IC Y Z omega squared EX plus IC YZ omega dot plus IC XZ omega squared EY okay. Okay, I think now we have everything we need. So this is what is kind of a general summary of the kinetics of a rigid bodies, that we need the two balance laws, balance of linear momentum and balance of angular momentum, to solve for the motion of a rigid body. And we should be able to calculate all the parts of this equation. Any questions? Yes?
Is the expression you wrote HC or HC dot?
HC dot. Anything else? Okay, great. So let's look at the first problem in set to 20, fixed point rotation. Problem 629 from NKB. So the uniform 100 kilogram beam is freely hinged about its upper end A and is initially at rest in the vertical position with theta is equal to 0. Determine the initial angular acceleration alpha. Welcome. Okay. The uniform 100 kilogram beam is freely hinged about its upper end A and is initially at rest in the vertical position with theta is equal to 0. Determine the initial angular acceleration alpha of the beam and the magnitude Fa of the force supported by the pin at A due to the application of the force P on the attached cable. So I don't want to actually solve this problem. What I want to calculate is not just the initial angular acceleration alpha. I want to determine the equation of motion of the bar. And then find an expression for Fa, the reaction force at A, as a function of time. Not just initially, but at any time. So take a minute, think about this, chat with your neighbor. Let's come up with a strategy to solve this problem. Yes, but O needs to be fixed. So the velocity of O and acceleration of O need to be 0. Yes, it needs to be fixed material point on the rigid body. Okay, so any ideas? What do we do? How do we solve this problem? We want to find the equations of motion of the bar. How many degrees of freedom does this bar have? How many? Show me with your fingers. Who says 1? Who says 2? Chat, discuss, take a minute, think about it. 1 or 2 or more. And then why? What are the constraints imposed on the bar? Okay, so how many degrees of freedom? 1, right? 1. If I know the angle theta and how it changes as a function of time, I know the whole location of the bar, right? So this is right. It's a rigid body, but it is constrained heavily, right? It's moving in the plane, so, and it's pinned at A. So there's only this rotation that's allowed, angle theta. So 1 degree of freedom. So how many equations of motion should I expect? 1. How do I get that equation of motion? First, can you draw the free body diagram of the bar? How many forces are acting on it? 3 or more. What are these forces? What are the forces acting on the bar? Yeah? What are they? Yeah, Fa. The reaction force at A. What else? The weight at the center of mass of the bar. Calling that D, because I have C already. And what else? The tension force, P, which is going to be along the cable, right? Okay, so how do I calculate the equation of motion of the bar? balance of angular momentum, about which point, which form should I use? About point A. Yeah, that's a good choice. Why is it a good choice? A is a fixed point, so I'll be using which form? B, right? But why is it good to sum the moments about point A? Exactly. So I hide the moments of the unknown reaction forces. Okay? So MA is equal to H dot A. A is a fixed point. A is a fixed point. Okay. How do I calculate the sum of moments about A? I want to apply this equation. Let me calculate MA separately and H dot A separately. If I want to start with the MA, how do I calculate the moments of all the forces about A? R cross F. So I'm going to start with the moment of the weight. That's what? RD minus RA crossed with the weight, right? What is the moment of the force P? How do I calculate it? What is it? I just need the expression right now. RP minus RA. Let me add this point. Maybe I'll call it E. RE minus RA cross P, right? Maybe I'll add a co-rotational basis on my rod. Maybe that'll make the problem a little bit easier. EX, EY. Notice how I've taken EX, EY co-rotational and EX, EY fixed so that I always have that EX is equal to cosine theta EX plus sine theta EY. EY so with the defined angle theta, the equations that I know I can still use here. Okay, so what is RD minus RA, this position vector? What is it? L1 EX, right? Crossed with the weight. What's the weight? Yes. No, the weight, oh, RD minus RA, right. So half L1 plus L2, you're right. What's the weight? What is it? mgEx. What is the axis of rotation in this problem? Easy, it's outside the page, right? And that's what we're doing for all problems in this class. We're always taking the axis of rotation to be fixed along EZ. Okay, what about RE minus RA? What is that? What is this vector? L1EX, perfect, crossed with P. Now P, what is P? So P is along the rod. How do I find P? Okay, yes. So this drawing is not my best, but however, this triangle here is isosceles because these two sides are equal. So this angle here is what? Pi by 2 minus theta. And these two angles are equal. They're equal to what? Right? And then here in this triangle, that's a right triangle, right? Correct? What is this angle? So then what does this angle become here? So that when I add these three angles, I get pi. I think it should be pi by 4 plus theta over 2. So when I add theta over 2 plus theta over 2 minus theta, yeah, I think it's this, right? So what does the force P become?
Magnitude P
Mm-hmm.
time cosine 4 plus theta.
Mm-hmm. Oh, yes. So this is EY, this is minus EX. Okay, so please go ahead, take a minute, calculate these cross products. You already know what the expressions of EX and EY is. So take a minute, calculate these cross products. Any questions before we do that? Okay, go ahead, calculate the cross products. Oh, these two lines are equal because they have the same length. This is 3 meters and this is 3 meters. Okay, so what's the answer gonna be? Any questions? Half L1 plus L2 mg small ex cross big ex is equal to what? Small ex cross big ex. So this cross big ex is equal to what? I cannot hear you guys. Are you sure? So this cross big ex minus sine theta. Do you agree? Yeah? Easy. Okay, then I'll have the plus L1 times P cosine pi by 4 plus theta over 2. Okay, what is small ex cross big ey? Small ex cross big ey is cosine theta az, right? And then this one, small ex cross big ex is what? Right. Okay. So that's the first part of the equation, the sum of moments about A. We should be able to do this without any problems, because this part of the equation is what we learned from statics, just calculating the moment of a force. Deal? If you have any questions about this, please pass by office hours today. Try to redo this problem on your own, all the problems on your own. Okay. Now I want to go to the other side of the equation, calculate the angular momentum h dot A. Okay, so h dot A, same expression as h dot C, is going to be IAXC omega dot, which is theta double dot, minus ICYZ theta dot squared EX plus ICYZ theta double dot plus ICXC. Okay, now it's going to be A, not C. Okay, this should be it, right? So what do I need to calculate here? Theta dot is part of the unknowns, the degree of freedom of the system. So I need to calculate the terms. Which terms do I need to know? Yeah, which terms do I need to determine? What are they? The inertia terms, right? So I need to find IAXC, IAYZ, IAZZ. Okay, what are these? So this shape, the bar, I'll go to my tables. this shape, the uniform slender bar, can I find it in the tables? Is it present there? Yeah, I can see it. Okay, so which moment of inertia do I want? I want all three. Let us start with IAZZ. Is that value given in the table? What is it equal to? This you should have from before, and it's on the website. What is IAZZ? For the uniform slender rod. Yeah. Uniform slender rod. What is it equal to? IAZZ. Can we find it in the tables? What is it equal to? Think a minute, chat with your neighbors. What is IAZZ equal to? Yeah, so what is it? What would it be equal to? Well, 1/12 if the axis of rotation passes by the center, right? What if here the axis of rotation doesn't pass by the center of the rod? No. It's perpendicular to the rod and it passes by its end point. So what is the moment of inertia IAZZ? 1/3 the mass of the rod times the length of the rod squared. Okay. What about the other two terms? Let's start with IAXZ. What is IAXZ for the rod? What is IAXZ for the rod? Why is it 0? What is it? Why? Okay. So remember IAXC, I can use the parallel axis theorem for that. It's ICXC minus AXAZ times M. Okay. And what is the moment of inertia ICXC? ICXC, that was the integral of XC dm over the rod minus M AXAZ. So for the rod, this is the center of mass C. This is the position vector of all points on the rod. EZ is out of the page. So what is the Z coordinate of all the points on the rod? Almost 0. So this is 0. Also AZ is 0 because the Z coordinate of this vector relative to this, which is the vector which has coordinates AX, EX plus AY, AY plus AZ, EZ has AZ 0. So this is 0. Another way to think about it is that because of symmetries, even if Z is not 0, for any point with coordinates xz, you have another point with coordinates x minus z. So these sum to 0, and this is definitely 0. So this product of inertia is 0. What about IAYZ? IAYZ. Also, it's going to be also 0 for the same reason. Instead of x, I'll put y, but still z is 0 and az is 0, so that's going to be 0. So the derivative of the angular momentum actually simplifies. Any questions? Questions? We're going to do another problem right now, where the products of inertia are not going to be 0. Yes?
And so you included the theta dot with the z term?
Theta double dot.
Theta double dot?
Oh, yes, it should be there. That should be omega dot. I'll fix it. Okay. Any questions? Any other questions? So these terms are all 0. So what is my equation of motion now for the bar? What is my equation of motion for the bar? Yes, I will plug in. So MA is equal to H dot A. MA is all the term I found over there. I will not copy it. And H dot A, here it's just going to be 1 over 3 ml squared theta double dot EZ. So once I project this along EZ, I'll get my equation of motion. It's going to be a differential equation in theta, right? Now, the problem was asking for the initial angular velocity of the bar. So initially, the bar is released with theta is equal to 0. Theta dot is equal to 0 because it's also released from rest. So if I wanted to find the initial angular acceleration of the bar, what would I do? The bar is released with theta is 0 and also released from rest, so theta dot is 0 initially. What is the initial angular acceleration of the bar then? How would I find it?
Solve for theta double dot.
Yeah, exactly. How? I already have an equation for theta double dot, right? The equation of motion. So I would just take the equation of motion and set theta 0, theta dot 0, and solve for theta double dot. Okay? So what would the initial theta double dot equal to? Okay, when theta is equal to 0, sine theta is 0, fine. Then I'll get cosine pi by 4 cosine theta. So that's cosine pi by 4. Sine pi by 4 theta 0. So I'll get L1p. So only this term will survive on this side. The cosine pi by 4 cosine 0 is 1. So cosine pi by 4 L1p EZ is going to be equal to 1 over 3 ml squared theta double dot. So that's how I find my initial angular acceleration. Does that make sense? Okay. Now, how do I get the reaction force at A? I still want to calculate the reaction force at A, FA. How do I calculate the reaction force at A? Take a minute, chat, think what we do. How do I calculate FA? Okay, what do I do? How do I calculate FA? I could take the sum of moments about a different point. That's not going to be enough. I don't think it is. Why is it not going to be enough? Yeah, FA has two components, and the balance of angular momentum here is going to have, it's always going to be along EZ, so you're going to need another equation. So what other equation can we use to find FA? the balance of linear momentum, right? F is equal to MAC. F is equal to MAC. Okay, sum all the forces. So that would be FA plus the weight, which we already figured out, plus P, which we already figured out. So FA is our only unknown here, is equal to M. How do I find AC? The acceleration of the center of mass. We found the angular acceleration of the bar. So technically, we have this differential equation. I can integrate it on MATLAB numerically, Python, whatever, and I can find theta as a function of time, theta dot, and theta double dot as a function of time. So if I have the angular acceleration, how can I calculate the acceleration of the center of mass? What is it? No, vectors. What is it? So AC, I can relate the acceleration of two material points on the same rigid body, right? So here, that's MAC, and AC minus AO is equal to what? Alpha, which is theta dot EZ, right? X or RC minus RO. Yes, double dot EZ. Plus omega cross RC minus RO. So that's going to be theta double dot EZ crossed LEX plus theta dot EZ cross theta dot EZ cross LEX. And now we see why the alpha L thing is very wrong, because you don't have this term in it. What is AO, acceleration of point O? 0. It's a fixed point, right? So I can find AC. So we're using the rigid body kinematics. Really nice problem. We're using a lot of what we learned. And I can find FA. If I have theta and theta dot and theta double dot as a function of time, I can find FA as a function of time. I mean, you can think about during the motion of the bar, there are some instances where FA is going to be minimum, and some instances where it's going to be increase or decrease or change. It's not going to be constant. Make sense? Okay, make sure your neighbor understands this problem while I erase so that we move on to the next one. Right. Any questions before I erase? So I'm changing this problem a little bit. I'm using L1, L2, and L3, and I'm putting the origin down there. So I'll read the problem in a bit, but we're going to change it and then we'll solve it. Yeah, like the mass of the horizontal bar and the mass of the vertical bar. Okay? So the 30-inch slender bar weighs 20 pounds and is mounted on the vertical shaft at O. If a torque M is 100 pound-inches is applied to the bar through its shaft, calculate the horizontal force R on the bearing as the bar starts to rotate. So I want to consider the system to be the horizontal bar and the vertical bar, kind of this system. I want to consider this to be my system. And what I want to calculate is the reactions here. What kind of support do I have at the new origin O? Yeah, so what motions are constrained and what motions are not constrained? Yeah, it's only allowed to rotate along EZ, right? So I'm constraining translation. The origin is not allowed to, or the base of the bar is not allowed to translate, plus rotation is restricted. Rotations about any axis other than the EZ axis is restricted. So what kind of reactions do I have at O? If I have a restriction in translation and a restriction in rotation, what kind of reactions do I have at the base O? What is it? Exactly, a reaction force and a reaction moment. So I'm going to call the reaction force and a reaction moment. Now, because what is the direction of the reaction force? Yes, exactly. Why? The direction of the reaction force is along X, Y, and Z in all three directions, because the motion of the base is restricted along all three directions. I cannot translate the base along any direction. So FR is going to have X, Y, and Z components. Now this might be easily expressed either in the rotational basis or in the fixed basis, not sure yet. I'll just use the fixed basis for now. Maybe it's easier, I'll call this force R, like this, R. Okay, I might later figure out that this R is more easily expressed in the rotation basis if I add one. No biggie, I can just change the basis on which I represent R. Okay, what about the reaction moment? What are the components of the reaction moments? Exactly, along X and Y. Why? Because rotation is restricted in these two directions, right? It's not restricted along Z, it's restricted along X and Y. So I'm going to have an MRX EX plus MRY. Okay, again, I might later find that it's easier to express the reaction moment in the co-rotational basis. So I'm remaining open to that. Okay, so what I want us to do is, one, find AOM of bar. Of the system. How many degrees of freedom does this system have? 1 degree of freedom, angle theta, right? I want to find the equations of motion, then I want to find expressions for the reaction force and the reaction moment. Can we do that? So I want you to do this. I want you to first, how are we going to find the equation of motion? Any ideas? Yes, we're going to sum the angular momentum about which point? O. We're actually going to get 3 equations. 2 of them are going to solve for the reaction moment. 1 of them is going to be the equation of motion. So let's go ahead, work in groups 2 or 3. Find the balance of angular momentum. Step 1, calculate the balance of angular momentum about O. And be careful, not all the products of inertia are going to be 0. So you're going to have non-zero products of inertia. So go ahead, do it, and I'm here to help. Let's give like 10-15 minutes for this first task, then some time for the other task, okay? It's very important that we work on this together. So first write the equation, free body diagram first, write the equation, free body diagram, then write the equation, then just start filling in the equation, 2 sides like we just did. So yes, please start by drawing the free body diagram. And feel free to change seats if you don't have a person near you. Move around. Why is the weight force at the end of the bar? Why is the weight force the extremity?
I'm just marking it out.
But yeah, be careful. The weight force will be at the center. Oh, okay, I see. Like this bar is not at the center. It's the bar is off center. Perfect. Then the reaction force, reaction moment, and that's it. Where is your free body diagram? This force here. What do you think about it? If I'm considering the system to be the combined, these two combined, then this is internal, right? So I would encourage you to draw the system on its own without the support, and then that's the free body diagram. Okay. Oh, and you also need to add the applied moment to the free body diagram. Don't forget. Yeah. I just wanted to use the factor equations so that you don't make mistakes, okay? Yeah, so just be careful. You're doing great, but just, yeah, be careful with that thing. So what do you need to add here? The applied moment and the 2 weights, right? And remember, the weight of the horizontal bar is not, it's off a little bit far from the shaft, the vertical shaft. The shaft does not pass by the center of the horizontal bar, which creates a mass imbalance. Where's the FBD? Yeah, just remove the support when you draw the free body diagram. Yeah, when you draw the free body diagram, you need to isolate the system from the support. How is it going? Where's your free body diagram?
Oh, okay. Free body.
Where's your free body diagram? Yes. Add the weight of the vertical bar also and the reaction force and moment, and you're good. Free body diagrams. So I'm considering the system to be the horizontal and the vertical bar. That's what I asked you. Okay, that's your free body diagram. No, you see, you're considering the system to be the combined horizontal and vertical shaft. So any internal forces here, they don't come up in your free body diagram because they're internal. Just the horizontal vertical. So two weights of the horizontal, weight of the vertical, this couple, and the reaction force and the reaction moment at the base. So you remove the support and you put the reaction forces at the support instead and moments. Yes. Just at the weight of the vertical bar, the shaft. Could you consider the combined system of the... Yeah, without the support though.
Well, this one.
Yeah. How's it going? Where's your free body diagram? No, you see, it's a rigid body, so you cannot draw it as a particle.
Okay.
Yes, where the forces are applied matters. So you have to draw a horizontal bar, a vertical bar. And the location of the forces matter. Like one weight here, off center a little bit, weight of the vertical bar here, reaction force, reaction moment there, and then the couple applied. Okay? Draw, then let me see. Where's your free body diagram? Okay, what are the weights? Weight of the horizontal bar, weight of the vertical bar.
Oh yeah, to draw the.
Yeah. Okay. Cool. Then you can start,
I
the
don't
weight.
see the weight of the vertical bar anymore.
I'm changing the problem a little bit. See, I give you the mass of the vertical bar on the board.
I see. Okay.
Okay. Yes.
Static, really basic, but over some of the moments about the weight, and then we take into account the weight, the R. Do we care about that?
Yes, you add the couples. You add the couples to both couples. Yes. Shall we take a co-rotational basis? Let's agree on one in case you want it. I can take EX like this, EY this way perpendicular, and EZ up. It's a right-handed basis. Okay, we should be done with the free body diagram and now summing the moments about O. So I sum the moments of the forces about O plus the couples. I add the couples, which are pure moments. What is it?
Is M essentially like the
What do you think?
Well, since it's a coupled moment.
So what is the 100 pound newtons is a couple that's being applied on the bar. It's along easy, right? The reaction moment is a reaction moment due to the support. So they're different, right? Even the direction is different. And the 100 pound inches along easy. By the way, you need to convert this to pound feet. I'm coming. And the other one is along x and y. Okay? Yes.
I don't really understand like why we have this second moment here, like what the couple is.
Yes, it's a constraint couple that constrains. So this bar has a tendency, because the weight is off center, it has a tendency to rotate this way. Why doesn't it rotate this way? Yeah, like just you can imagine if there is no support, if there was a system like this, that it would just tip over this way. So it has a tendency to rotate this way. There should be a reaction moment provided by the support that makes opposite to that makes it not rotate that way.
So it has to be in the easy direction.
Yeah, well, this, because the bar is rotating, the direction of reaction moment is rotating. So it's gonna be more easily expressed in the rotational basis. So you're gonna see, but it's the same concept as a reaction force. If I had no reaction force here, then this system would probably just fall down. I need a reaction force to keep it from falling down the table, and I need a reaction moment to keep it from tipping over. Okay. So for example, if I look at a pin here, there is no rotation constraint. It doesn't constrain rotation along this axis. So the bar is just free to rotate about this axis. However, this support constrains rotation in the plane like this. So I need, and outside the page, along x and y. So I need a reaction moment to satisfy this constraint. Whenever I have a constraint, I need some reaction force or moment to satisfy it. If it's a translational constraint, then it's a reaction force. And if it's a rotational constraint, then it's a reaction moment that is needed to enforce the constraint.
So, like, this moment already being applied, does that not already help with, like, it not
This
tipping?
moment is along EZ. And what it does is that it makes it rotate along EZ. But still, it doesn't affect the tipping over.
Okay.
Yeah.
And this, so, like, if it were to just tip in theory, oh, I guess it would tip at, like, an angle, so then it would be in...
It will. So this is gonna rotate along the vertical, and the tipping is gonna be along some direction along the horizontal plane, in the horizontal plane.
Okay. And then...
Does that make sense to you? Do you have a better way of explaining it, maybe?
No, that makes sense. I think it's kind of similar to the midterm question 3, was it, where you have kind of the off balance thing on the rods.
Yeah,
when you like spinning
masses.
around.
Yeah. It's the same system. Actually, it's a very similar system.
Okay.
Yeah.
And then also when you're trying to write, like, in terms of L1 and L2, if
Mhm.
you're trying to write the weight, I don't really, like, it would be applied at, like, 1/2 L1 plus L2, but how do you express that relative to, like, the
Yeah.
origin?
I think 1/2 L1 plus L2 is this distance. So you have to subtract minus L2 to get that. Right, so you want just the distance between the origin and the center of mass. The distance from the end of the bar to the center of mass is 1/2 L1 plus L2. So if you want just this, you maybe need to subtract L2. Maybe I'll draw it on the board. Yeah, so I have this. this is the distance you want. Okay, I'm gonna look around, check out how you're calculating the sum of moments. Are you calculating the sum of moments? Do you calculate that?
I'm trying to. I don't know if I really got it right.
The moment of the horizontal weight plus mr plus m. You need to add m. This here. Yeah, that's good. So A is where the weight is applying. Yes. Plus L3, L1 plus L2 over 2. What is this?
This is the.
Oh, okay, you have to be careful. So, L1 plus L2 over 2.
Is the distance of where the.
Yeah, it's like the length of half the rod. But you want this distance, not that distance. So if you see on the board, L1 plus L2 over 2 is the length of half the rod, but you want the distance between like the yeah.
Okay.
You're welcome. Okay. Have you calculated the moments, the expressions at least? Sum of moments about O? Not yet? Where is it? Where is it? I want to see it. Why is it half L2 minus half L1? Why this?
Because this is like 1/2 L1 plus L2.
Mm-hmm.
And then so this section is L1 minus 1/2 L1 plus L2. And then since I defined EX to go that way.
Okay. Okay, plus you have to add the reaction moment.
Oh yeah.
Okay? Double check he has the same answer. Okay, make sure he has the same answer. Have you calculated the reaction moment?
This.
Okay.
I didn't do the cross product, but.
Cool. Okay. The cross product, I don't think it's going to be too bad. Probably will keep it in the quotational basis. Can I see? Oh. So, okay, be careful. You have to convert the 100 pound inches to pound feet, right? To US customary units, pound feet. So divide by 12 to make it into feet. Okay. And it's along easy. That is along easy. You never can add vectors and scalars. Good job. Okay. So L3. This is not right. This is not right. If you can ask him about it, but this is not right. Oh, this is the vertical one.
Doesn't matter where it's applied.
Okay. L3 over 2, easy plus easy. Anyways, it's going to be 0.
Applies them.
9 EX plus L3 easy. Why is it 9?
This is the what's it called?
30, 15. 15, it's not 9.
The 9?
It's not. I don't think it's 9. Double check. Because it's, so 30 divided by, it's 15, and 15 is going to be 3 inches this way. So 3 over 12.
Also with easy, it'll be.
Oh.
Yeah. Why do you have another one too?
And make sure you also have your reaction.
One for the vertical, one for the horizontal.
This
But it needs to apply to
Oh, you separated two sides. Okay, that's fine. That's fine, but be careful. You have to use feet, not inches. Okay. Plus the reaction. You have to add the reaction moment.
Reaction
Okay.
moment.
This one?
Yeah.
No,
Oh,
No.
is it?
That moment.
that's the sum of moments about O, which includes the reaction moment. Okay.
Truly out and other easy.
What's MO?
Summer moments about me.
Yeah. Can I see it? Can I see it? Oopsie, sorry.
So pure moment.
Okay, looks good.
moment.
Looks good. Where is your sum of moments?
So when you wrote the parallel axis theorem for the products of inertia, you wrote AX and AZ. What are those two quantities?
Oh, they are the components of the position vector between the center of mass and the point we're trying to find. Yeah, but can I see the MO for you? It's MEZ plus W1 plus W2 plus. Okay, and you have to add the reaction moment plus MR.
Oh, the reaction.
Yeah, there's
the
this.
reaction.
There's this M and there's MR. Do you have any questions for me?
I think I'm about to finish. Maybe.
Okay, can I see where you're calculating the reaction moment? Just the expression. Sorry, the sum of moments about O. Sum of moments about O. But I want the expression initially. Sum of moments about O.
Sum of moments about O is. There's this one.
Yeah.
And assume they got like the other two directions.
Mm-hmm.
And just through calculation, it should. We should get the other parts should cancel out, like this moment and
The moment of the weight is not going to be zero, not for the horizontal bar.
what?
The weight of the horizontal bar, it's not going to be zero. The moment of it is not going to be zero.
Yeah, I know. Yeah. I mean like.
Can you write the expression and show it to me? Can I see?
Sure. So then this is the.
How are you crossing a scalar with a vector?
Sorry, I put in the EX after for the quotational basis.
Okay. Yeah, but put it here too. Looks fine. Can I see how you're calculating the moment?
I was kind of confused on how to do it for the weight.
R cross F. So the weight is applied here. You're gonna have to find the position vector from origin to there,
So is it
crossed
just
with the
all
weight.
the EX?
Yeah.
So
Well, it has a vertical component as a horizontal component. The vertical component will cancel out eventually.
So are the only moments applied on the system the weight and the couple?
And the reaction moment.
But I thought since it's at the origin,
That's if it's a force. The moment of a force at the origin. So the moment of the reaction force at O is zero. But the couple moment is not gonna be zero.
I didn't even use it. Oh yeah, like the couples one.
Yeah, so there's this couple, and then there's the reaction couple due to the support.
Oh, okay, I see. Oh, we don't know that. We should click unknown.
Yes, it is unknown, correct. How we doing?
Yeah, we're just discussing how to do it. So
Okay, can I see your expression for MO?
we're just looking for like what we're writing down for like the inertia.
Okay, but I just want to check this first. MO is MR minus MG. Blah, 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 blah. I don't think that's correct.
Oh, that's not correct.
And it's never the force crossed with R. If you were to do that, you offend the course. You cannot. It's R cross F. Always position cross force, okay?
Oh, it's opposite. Okay, gotcha.
And what is FG1?
FG1. Oh, it's just like the force of this thing, of like this bar. Like the
What
of gra-
force?
The force of gravity of the big bar.
So
just
that's
like-
for the vertical bar?
Yeah, for the
Oh, so that's along EZ.
yeah.
And it's also EZ crossed with EZ. It's going to be zero.
Oh,
Fix it. Fix the moments. You need to calculate the moments correctly. Sorry, thanks. So MO, what is MO?
So we have the center for the bar, so that's L1.
But be careful, because this is the center from the end of the bar, but you want it from O, which is here.
But would it not still be acting upon here and then the one for this?
Yeah, but the distance between O and this is not L1 plus L2.
Yes.
So it's L1 plus L2 over 2 minus, for example,
Minus
this
L1,
one.
okay.
Yeah. And
That
then MZ and oh, this is it. Oh, this is it. This is correct.
Yeah, but that's so it's the exact same equation for this bar and that.
Okay, so this is, I'm assuming, for the vertical bar.
Yes.
Okay, so you don't need this L1 plus L2 over 2 thing. So it's just L3 over 2, easy. Yeah, and this is, easy is the vector here, not M. And MR, this is good. So this is L3, not L3 over 2.
Sorry, I got really stuck.
Okay, where's, you have your feedback diagram? Yeah, it's on the board, right? So how do you calculate the sum of moments about point O? How do you calculate the moment of a force? You sum, first of all the couples, then the moments of the weights about this point. Yeah, the weight force. So you have a weight here and you have a weight. Wait, can you see the board from here? Do you want to glance it over there? Oh, you can see it? Okay, I can see it well. So you see the weight that's off center for the horizontal bar. How do you calculate the moment of that force about O? Yeah, so it's always the position vector from O to the force crosses the force. Yeah. So the vector from O to the force crosses the force. Good. What about the angular momentum part?
Oh, yeah, I haven't done that part yet.
Okay, come on. Okay, did I check your work?
Wait, I'm confused about how to find the products of inertia after.
Okay. The products of inertia above the center of mass are 0. Maybe use the parallel axis theorem.
Okay.
Above the center of mass are 0, but you have to calculate this AX, AY, or AY, AZ term.
Oh, I finished.
Did you get the same answer?
Yeah.
Can I see your work? So where is the expression for MO that I needed you to get?
I think, do we really care about what MO really is?
Yes, I asked for it. I want you to find not that's just R. I want you to find the reaction moments
Oh, okay.
and the reaction force.
So forces.
So I want you to calculate the products of inertia, everything.
Okay.
Okay, so I'm assuming we're all calculating the angular momentum part right now. The angular momentum. Any questions? Yes.
So I got something for the moment due to this force. The moment due to this force is 0. This force is 0. And we don't know MR. And we also know that there's 100.
Yeah.
Okay.
But I don't care about the numbers. Don't spend too much time on the numbers right now. Find the expression. Sure.
So I'm still stuck on this part right here where I'm from.
Products of inertia. Yeah.
Kind of lost as to what I'm supposed to do.
Okay. So what are AX and A? Yeah, the components of the position vector from like the center of mass of the bar to where you're trying to find the moment about.
The center of mass of the horizontal bar.
Yeah.
Okay. So from the origin to the horizontal bar.
Yeah.
But then these are the lengths of the horizontal bar.
No, these are, well, this whole term is 0 because x, z are the components. If you take a differential mass on the horizontal bar, x, z are the components of the vector from the center of mass of that bar to like any point on the bar, and you're summing for all possible x, z on the bar.
It's like a uniform mod.
Yeah, because it's a uniform rod, all of these points have coordinates. Z is yeah, have coordinates. Yeah, Z is 0, where the center is the origin is taken at the center of mass. Yeah. So this IC XZ is 0. Now we have to calculate the AX and the AZ. Yeah. O is at the bottom, right? Yeah. Yeah. So the moment of inertia of the system is the moment of inertia of the vertical bar plus the horizontal bar. Now the vertical bar has no mass distribution about EZ, so moments of inertia of the vertical bar is 0. So all you need to think about is for the horizontal bar. Okay? So you'll definitely need to use the parallel axis theorem for the moment of inertia and the product of inertia. So it's the same ones we need, but you're going to use the parallel axis theorem for the moments and for the products.
There is 3 different moments in this equation for the quantum moments, right? So there's 3 different moments.
Yeah.
Any questions? I need you to calculate the reaction
60.
moment.
60.
60?
Yeah.
It's supposed to be a vector.
60 y, so it's along the y direction.
The rotational or the fixed y direction?
Huh?
Rotational or fixed?
Rotation.
Okay, good. What about the reaction force?
It's just 3.57.
But it's supposed to be a vector.
Along negative. So it's negative. Is it? Oh wait, I lost it. Negative EY direction. Is it?
Shouldn't there be reaction force along EZ also?
Easy is wait. Is there? So easy is the one counteracting the weight.
Okay.
Yeah.
Okay. Do you want to do the next problem?
Oh wait.
Any questions? Anyone? So what is the moment of inertia? What is the moment of inertia as the ZZ? Moment of inertia about O, IOZZ. What is it going to be? What is IOZZ? Does anyone have it? Can I see it? It is long. So it's the 1/12 ml squared plus, yeah. Good. What about the products of inertia? 1 is 0.
YZ 0 and XZ.
This one has no x.
Okay.
This be 0.
Yes.
Isn't there a Z up here? Isn't
For-
L3 there?
Or no, this one has no x.
That one has no x and y.
And this one has no z.
But it has a z though. It has this.
Any questions? Anyone?
The bar.
Are we all
But it
at
has no
calculating the
mass distribution.
moments and products of inertia? Are we all
Right.
doing
Because
that?
it's a sum over dn.
Yeah, but are you taking the inertia around O?
What's going on?
For I x z
Mm-hmm.
is, does the horizontal bar have any z component?
What do you guys think?
Well, are you taking the inertia around O?
Yes.
Or around,
Oh,
around O at the base.
yeah.
It would have
Yes. Yes. Okay. Come on, quickly. Come on. Done?
No, I was curious. If we have the moments of inertia at a certain axis, two pieces individually,
Well,
we just add them linearly.
Gave like
Seems
use
kind of
nh and nv.
Can you repeat the question?
So if we have the moment of inertia
For us.
horizontal
What?
bars,
For nh and mv for the mass of the
Yes.
bar and the rod.
Because how do you calculate the moment of inertia? You integrate. So it is a sum.
So assume that you know,
Yeah.
but
But for the vertical body, the moment of inertia is going to be 0.
yes. But I was just thinking because
like I don't even know.
the moment of inertia, like the product of inertia, that kind of stuff. I want to do it about the center
You
of
might
mass
be able to
and then
solve
do
this by
the change
using
of axis
just
to
But
this
same.
point.
Okay.
But I don't entirely see
So I
how
guess
to
that
do
I would just consider the horizontal bar now without the vertical bar. Yeah. Yes, but you're right. It is a sum. Okay, whoever's done with this problem, is anyone done with this problem? Okay.
Don't we need the thickness of the bar as well? Like the
No, you're assuming no thickness because it's slender.
Oh.
Yeah.
There's two components in the one.
But why would you need the thickness?
Oh, I guess I would. Yeah, that's a good point. I was just thinking because the formula goes a squared plus b squared. I guess if we set b to 0, then
Yeah. But also you have a uniform standard bar in the
yeah.
yeah.
I guess so we're doing the integral to get rid of I.
Yeah, I think this is the section.
Yeah.
When I'm trying to find IZZ, I'd have to use parallax system. So I'd say the moment of inertia through the center of mass and then offset it by the distance of
Yeah.
which we found earlier, which was like this one, right?
Yes.
Okay.
Yes.
The formula for it is
You don't use the easy component of the distance though, it's just the x and y, right?
Yeah.
Yeah.
Just the x and y components.
Yeah.
Is formula m
Mm-mm.
is the total mass of the bar?
Yeah, that's why. Yeah, m is the total mass of the horizontal
So
bar.
the horizontal
Yeah,
right?
but that's why I don't use this because what is d? It's gonna be for us just the horizontal distance, but here they're assuming planar motion, so there's no vertical distance anyway. But anyways, you can look at the equations of the nodes.
Professor?
Yes.
Okay, so I think I might finally have the products of inertia.
Great. Now what are ax, az, and ay?
Those are just the, well, I haven't,
The x, y, and z components of what you just these
they're just
this vector.
but they'd be like this purple line, no? From the
The x, y, z components of this. So x is non-zero, y is 0, z is non-zero. They're the x, y, z components of this vector that you had, this one.
X, Y.
Yeah, so it has x components, z, but not y. Yeah. How are we doing? Products of inertia, moments of inertia. Any questions?
So, because the bar is uneven, typically we treat the bar as like a whole if like it's rotating about the center. So since it's offset, do we like just do it twice?
You can do it as a whole or you can do it two parts, both parts. Yeah.
And then there's no thickness to it.
No thickness to it, right? There's no thickness. It's we're assuming it's a uniform slender. It's a slender bar.
Oh, just slender.
Yeah. But why would you need the thickness though? Do you need the thickness? Oh no, yes. Then there's no thickness. You can easily see the slender bar here at the end of this page. Yes.
Like at if it's
Gentlemen, how are you doing?
So essentially, you said earlier the product of like inertias are not going to be zero.
At least one of them is not going to be zero. That's right.
So which, because like essentially like for
You tell me which one.
the thickness is just zero, like the thickness is
Yeah. So the.
and they're all in the z there.
Yeah, so the moments of inertia about the center of mass, the products of inertia about the center of mass are going to be zero. I see x, z, I see y, c. They're zero. So these two terms, these are zero. But yeah, you have not, they're not areas, they're distances. These are the components of the position vector between A and C, right? They're components of a position vector. So C is the center of mass of the body, the horizontal bar, and A is here is O because you're finding the angular momentum about O, the moment of inertia about O. Okay, you finished the angular momentum.
Yeah, I went ahead and found the angular acceleration.
Great.
And then,
Can I see?
sure.
So what were IOXZ, IOYZ, and IOCZ for you in your case?
Yeah, I went ahead and,
Can I see them? Do you have them calculated?
oh, sorry, which ones?
The moments of inertia, the products of inertia.
Oh, yeah, I didn't do the products. I just went ahead and, for
angular acceleration, just went ahead and dot product by EZ.
Right, but if you want to calculate the reaction moment, then you need to calculate the products of inertia.
That's true, yeah.
Which I want you to practice doing that.
Gotcha, yeah.
We'll talk about this in office hours, okay?
It makes sense to me. It's just putting it.
Okay. Step by step. It's okay if it's slow, but step by step. Any questions?
So, because it's linear, we're assuming there's no vertical component, right?
For the thickness of the bar?
Yeah.
Yes, right. But I don't think it would matter. Any questions? Anyone? Questions? Yes. Not the x. I think the y is going to be 0.
Okay, yeah, because I was thinking
Oh, no. The x moment. Wait.
sorry, the product of inertia.
The product of inertia. The y one is going to be 0.
Okay.
Do the calculations. It's because a y is 0.
Oh, right, because the center of mass. Okay, the only part that contributes should be the x distance and then the z distance here, so it should be 1 minus L2 over 2 times the height is
L3. So that's ax. Right, exactly. So ixz is not 0. Iyz, it's L3 times z.
Yeah. YZ, that would just be. This is 0 for this one because it's symmetrical. I think, yeah, the whole thing is symmetrical, so it should just be 0 for YZ, right?
Use the formula.
Okay.
What are you looking at?
I'm just kind of trying to understand the actual relation between calculating.
So these equations I don't like because they make a lot of assumptions. One of them that the products of inertia are 0, that the rotation is along easy. So if you could use the equations we have on the board, the same ones I taught you, would be great.
Is somebody using nail polish? Sorry.
Yeah, I smell it, but it could be.
Leaking on somebody.
So just write the equation you want. Then the next question is, okay, how do I calculate each term? Okay, are we done? Done with this problem? Fini? Done? Questions? How's it going? Done? Great. I will check it in a bit. Are we done? Any questions? Done. What we doing?
We're working through the products of inertia.
Okay. What did you get for the products of inertia?
I got IZZ.
What about YXY and IYZ?
Yeah.
Oh, still, guys, running out of time. Okay, you had figured out the products of inertia, moments of inertia, right?
Yeah.
Yeah. Okay. Okay.
And then I had HO,
Yeah.
the product of inertia term, and this is the moment term.
Yes.
And then I projected it.
The reaction moment only has an x component, not a y component.
Doesn't have a y component?
Okay, seems like it does. Okay.
It just doesn't have a z component.
Yeah.
And then once I got
Well, we already knew that the reaction force has a z component. The z component, so the projecting along the z gives you the equation of motion. And then F equals mac, and you calculate ac this way. Why is that a dot zero? Only initially, if it's starting from
yeah,
rest.
I just did it initially because I wanted to just get a final answer instead of
Okay.
a long equation.
And
Make sure I did
then,
it right.
okay, cool. Yeah, and then you can write the reaction, find the reaction force, and they only want the horizontal component of it, x and y. Okay,
alright.
cool, good job. Okay, so we're gonna pause this problem a little bit. I just wanna explain a concept called the center of percussion. That's related to problem 651, okay? And then you can finish this problem. I have a solution video for this problem we were just working on. So you can finish it, look at the solution video. If you have any questions, let me know. The rest of these problems, you'll solve a lot of them in the problem session, exercise discussion section tomorrow. But I do want to discuss problem 5. We will not solve it, I want to discuss it. Maybe we'll solve it, we'll see. So a device for impact testing consists of it. So problem 5, the same set. A device for impact testing consists of a 34 kilogram pendulum. Yes, it is kind of a pendulum, with mass center G, with radius of gyration about O of 620 millimeters. What does that mean, radius of gyration about O? What does it mean that the radius of gyration of this pendulum about O is 620 millimeters? Not quite. Because the center of mass is 600 millimeters, right? Yeah. What is the radius of gyration? We kind of explained it quickly before. Remember, sometimes instead of giving you moments of inertia, they give you radius of gyration. Where does the term radius of gyration come from?
An equivalent circular.
Yeah, the moment of inertia of a circular hoop. Okay, so how do I calculate the moment of inertia of this system? About ZZ, IOZZ, it's going to be m times the radius of gyration squared. Okay, the distance b for the pendulum is selected so that the force on the bearing O has the least possible value during impact with the specimen at the bottom of the swing. Determine b and calculate the magnitude of the total force R and the reaction bearing it. Okay, we can select this distance b between kind of where the impact is happening to minimize the reaction force at O. How come? Can you think about it a little bit? How come if I change what this distance b is, the reaction force at O might be minimized or changed? Okay. To think about it, what I want you to do is, can I borrow your pen? Everyone take a pen in your hand. Okay. And hold it up top. Take a pen, hold it up top. Okay. So if I push the pen, strong force from below, like this, where do you feel the reaction force at the top of the pen needs to be? In which direction? So that it doesn't go. I feel like it's, I feel like the pen is tending to move this way, right? So the reaction force needs to be that way. However, if I take this pen and if I strike it up here, what is the direction of the reaction force going to be? Opposite, because I feel like the end of the pen is tending to move in this direction, so my reaction force is going to be in the opposite direction. Let me draw it on the board. Okay, I take the pen, it's pinned. I strike it here, sorry. What is the direction of the reaction force going to be due to my striking of the pen? It's going to be in this direction because the pen is going to tend to move like this, right? So my reaction force is going to be in this direction. Does that make sense? Do you see it? Test it, try it. Whereas if I impact the pen over here, the pen is going to try to displace like this. So I'm going to have a reaction force in this direction. Does that make sense? Does that try it? See it? You can even try to look at the pen without any constraints, without constraining it. So if I look at the pen here, if I strike it from below, the top is going to move to the back. But if I strike it from the top is moving to the front. Somewhere, if I strike it in between somewhere, yeah. So the idea is that the reaction force at O, the reaction force at the pin, depending on the distance between the impact force and O, the reaction force at the pin, if it's too high, if the distance between O and the impact force is very high, then R is going to be in some direction. If the distance is very small, R is going to flip. So the idea is that somewhere in between, the horizontal component of the reaction force due to the impact is going to be 0. So the whole reaction force at the pin is going to be minimized. Remember, I have other forces acting on the system. I have the weight. So I will have also a reaction force component due to the weight. So maybe R vertical, R horizontal. So at some point, the horizontal component of the reaction force flips. It's negative, it's positive, so at some distance it will flip. At this point, where just before it flips, just after it flips, when it flips, then it's going to be 0. Because it flips, when you flip, at some point you have to be 0 before you flip sign. If you're going from positive to negative, at some point you're 0. So this horizontal component of the reaction force is 0, meaning that the reaction force is minimized. So the location at which this happened is called the center of percussion of the pendulum, for example. So we want to find B such that the horizontal component of the reaction force is going to be 0. So that would locate the center of percussion, and that's how you would go ahead and solve this problem. Okay? So we will not do it right now. You will do it in the exercise session tomorrow. If not, I also have a solution video for this. But that's the concept. The idea is you want to solve this problem. You want to find B for which the horizontal component of the reaction force is going to be 0. Okay? Any questions? Yes?
I don't really understand why the reaction force is to the right. The second diagram.
Yeah, because when you impact the bar like this, the tendency to displace is going to be to this side. So the reaction force counteracts this displacement. Here, when you strike here, the bar is going to tend to displace like this. So you want the reaction force to counteract the displacement. Yeah, the reaction force is what's enforcing the constraint that this point O is pinned, it's not allowed to move. Yeah. Does that make sense? Any other questions? Okay. Thank you all for coming. See you on Tuesday. I have office hours. You can try to solve the problem yourself and figure out how F is going to be in the different situations.